Hi, we can get started. This is a review session for exam 2. I'm one of the TAs that teach in section 7 to 9. So the plan for, so let me know if you cannot hear me. Well, I may have to adjust some settings on the computer.
We can hear you.
Sorry, what was it? Okay, perfect, thank you. So my plan is that we can go through any questions you might have as you study for the exam. If you don't have any questions, maybe just take a quick look at the review sheet and maybe pick some problems that we can look at together. In the middle, if you have any questions, feel free to interrupt me, ask your questions. So let's see. So 3B, all right. I'm just gonna begin with 3B then. Can I write out all the topics that will be on the exam? That's a good question. Let me get my book. I actually, to be honest, I don't really know exactly the sections that will be on it, but I'm thinking the last time we finished 7. If I remember correctly, begin with 7.1, I believe. So this might be wrong, but I think this will cover most of the exam. Section 7.1. I think that's the first section will be covered by this exam, which is integration by parts. Just a quick review that this technique will require you to set up the full terms u du and then dv v. So the given integral. So if you take a given integral f of x, maybe g of x, that's probably not the best way. Maybe set it as u dv. That's a form of the given integral. So you know this part, and then the dv part. Then you can take the derivative of u to find du and integrate dv to find v there. After that, you can apply the formula of integration by parts, which is u v minus integral v du. So that's the formula there. And then 7.2. So I'm probably not going to list out everything, but 7.2 is trig integrals. Which there's a lot of techniques that you can use. You have to look at the exponents of sine or cosine. All the exponents of tangent and the cotangent, cotangent and the secant. And after that is 7.3 trig substitution. So that's a case that if you have something like square root of x squared plus or minus a squared in the denominator, in particular dx, doesn't have to be in the denominator, but if you have square root of x squared plus a squared, trig substitution works really well there. You basically have to set up a right triangle, call this angle theta. From there, you can derive an equation of x in terms of theta for the substitution. And then 7.4 will give you integration by partial fractions. Basically, you take a fraction and then you convert it into a sum of simpler fractions. Yes, this session is recorded, I believe. And then afterwards, whenever the link is available, I'll make sure the link it's published somewhere on Canvas. Right. And then 7.5, it's basically kind of a practice of 7.1 to 7.4. You know, given the problem, you kind of have to decide which technique is the best approach. You might have to use maybe integration by parts first, and then use trig substitution, or vice versa. You might have to use multiple techniques in the process. And then 7.8, which is improper integrals. That give you two cases. One is that you might have infinity or maybe minus infinity in the boundary values. This is what I've been telling my sections, that when you try to integrate this, don't just find the antiderivative directly. Make sure you use the correct limit notation. Say you can call the infinity t. So say we want to take the limit as t goes to infinity of the integral from a to t f of x dx. So make sure you apply the limit definition first, and then you can find the antiderivative and evaluate it from there. All right. So that's type 1. Type 2 is that, oops, sorry. If you just have integral from a to b, f of x dx, you might have an infinite discontinuity somewhere there. Could be at the boundary values or maybe somewhere in the middle. Then you have to break down the interval of integration. All right, and then in that section, you also have this comparison test. All right, with that said, let me begin with 3D, I believe. So that was a question about 3D. Make sure there's no messages I missed. Feel free to put your questions everywhere, so you can just type your message to everyone instead of a direct message. Either way is fine. All right, so 3D. So 3D, it says determine whether the integrals are convergent or divergent using comparison theorem. So here we have D given is from 5 to infinity, 1 over cube root of x to the 4th plus 8. That's a dx that's missing, I believe. Dx. So comparison basically saying that we don't want to use the definition of improper integral to rewrite it using limits, because it might be very challenging to integrate after that. But we can maybe try to find a function that we can compare with 1 over cube root of x to the 4th plus 8. The function could be above it or below it, but how do we find it, right? Now, here's kind of a trick. Whenever you have this fraction form, if you have, let's just take a simpler fraction on the side, then I'm going to erase it in a second. So let's just say you have, let's say 7 over 3 plus 5, right? And I want to compare this fraction with 7 over 3, for example. Which one is bigger? I mean, you don't have to think too much, right? You kind of knew it back then, maybe in high school or middle school. You know that 7 over 3 is bigger than 7 over 3 plus 5 because the denominator is getting smaller. So the fraction value is getting bigger, right? That's something you learned. So same thing 7 over 3 plus 5 is less than 7 over 5. So whenever the denominator, we remove a positive term, we make the denominator smaller, then the quotient, the fraction value is getting bigger, right? So in this given example, the denominator, even though we have a cube root, but we also have a x to the 4th plus 8. So I can kind of make it looks like that, basically. Think about the denominator has two terms. If I drop one term, say we drop the 8, for example. So I'm comparing cube root of x to the 4th plus 8 with 1 over cube root of x to the 4th. Right? Which one is bigger? Because the denominator is actually getting smaller when we drop the positive 8, we actually end up with 1 over cube root of x to the 4th power is bigger. So that's kind of something you kind of get better at this by doing exercise problems. But generally speaking, if numerator has multiple parts, you can play with it by dropping one term. If denominator has multiple parts, you can play with it by removing one term from the denominator. I'm going to put an equal sign there, does no harm. So basically, we're comparing the integral 5 to infinity of 1 over cube root x to the 4th power plus 8 dx with integral 5 to infinity of 1 over cube root x to the 4th dx. Why do we do this? Well, the reason we do this because this integral is a lot easier to find out whether it's convergent or divergent compared to the given one. So we know the given one is less than this one that I compared to. And I'm going to focus on this new one, and I want to know if this is convergent or divergent. Right. So how do we find out? Well, I'm just going to rewrite the fraction, the function given in the middle. I'm going to rewrite it as integral 5 to infinity 1 over x raised to the cube root is 1/3 in the exponent, so that's a 4 over 3 dx. And if you recall, this is the form of t-test, right, of t-rule. This part is basically the p-value that we're looking at. So in this example, p equals 4 over 3, which is more than 1. If p, the exponent p is more than 1, then we know the integral will be convergent. So here we found out that this integral is convergent. Right? So this integral that's bigger than the integral we're interested in is convergent. What about the one that's smaller than this? The one that we are actually looking for. So this given integral is also convergent. So this is what I kind of mentioned in my recitation. So you can look at this integral as area. So we know that the given area, so we're interested in the area from 5 to infinity. So let's say this is 5. So from 5 to infinity, we want to know this area. So that's what the integral says. We can't calculate it directly. So what we do is we find a function that ends up to be bigger than this. The function is this 1 over cube root of x to the 4th power. And we were able to calculate the area below this blue curve and found out that that area is finite because the integral is convergent. Now, if the big blue area is finite, what about the small green area that we were interested in? Well, that has to be finite as well, right? you cannot have an infinite area inside a finite area. That's just impossible. So the green area is finite, which means the integral is convergent. So just like I said before, generally when you look at comparison tests, if the denominator has multiple terms, try to drop one term, come up with a new function. If the numerator has multiple terms, drop one term, and come up with a new function to compare with the given one. If you have sine or cosine, for example, like a and a b in number 3, you can use the idea that sine is from -1 to 1 and then go from there. All right, there's more questions in the first part, number 1. So 1R here, or also I, okay. Let's see, R. All right, or you can look at 3A. But let me begin with 1R here. So what do we have? We have integral tangent to the 6th power 3x, secant to the 4th power 3x. So this one, again, is tangent and the secant. So I'm looking at the exponent. That's 6. This is 4. But the 4 is the more important one because if you remember, the rule says if the exponent of secant is even, we're going to save a secant square and set u equals tangent, right? So I'm going to do that. So tangent to the 6th power 3x. Secant, I save a secant square, so I have another secant square remaining. And I'm going to let u equals tangent x. So if I set u equals tangent, then immediately you can take the derivative. So du equals secant square x dx. But I'm not doing it correctly, right? Because I don't have the, if I see tangent x, it's not going to help me here. So I'm going to erase this. And instead, I'm going to say u equals tangent 3x, because that's what I have. I have tangent 3x. And then from there, du equals the derivative of tangent, which is secant squared. Sorry, but it's secant squared of 3x, right? But then I have to use chain rule because inside the secant or inside the tangent, I have 3x. So the chain rule tells me that I'm going to end up with the 3 dx. And from there, I can either solve for dx or solve for secant squared 3x dx by moving the 3 to the left. So I get 1/3 du equals secant squared 3x dx. And substitute in there. So I get integral 10 to the 6 is u to the 6th power. And what about the secant square in the middle? Well, you can leave it now, or you can rewrite it using 1 plus tangent squared 3x. And the second secant square dx, that will go away and being replaced it with 1/3 du. For me, I always move constants outside. So 1/3 goes outside. I have u to the 6th, 1 plus tangent square 3x, that's a 1 plus u squared du. And from there, you can distribute the u term, the u to the 6th. So I get 1/3 integral u to the 6th plus u to the 8th du. So from here, I'm going to do it a little bit quick because we're basically just finding the antiderivative. So you get 1/3 u to the 7 over 7 plus u to the 9 over 9. Plus a c. Right? But I don't want to have the u there, right? I'm going to write u is tangent So that's a 1/3 tangent 3x to the 7th power over 7 plus tangent to the 9th power of 3x over 9. You can distribute the 1/3 or you can leave it. I'm not going to bother to do anything after that. I think there was another question on 1s. Okay, any questions on that problem? All right, if not, I'm going to go to 1s. So here we have tangent to the 5th power of 3x secant cube of 3x dx. Now, again, I'm looking at the exponent. So here I have 10, it's odd exponent. Secant is also odd. So secant is not even, so the previous technique doesn't work. But the good thing is that here we have tangent as an odd exponent and the secant has an exponent as greater or equal to 1. And that's good. In this case, we're going to save one tangent. So we're going to save tangent multiplied by secant. And then we're going to set u equals secant. So let me write down what I have. So I have tangent to the 4th power of 3x after I save one tangent, and the secant squared 3x after I save one secant, then multiply with tangent 3x secant 3x dx. And I'm going to let u equals secant 3x. So du equals the derivative of secant. If you remember, it's just tangent times secant. So tangent 3x times secant 3x dx. Well, before I write down dx, I forgot to use chain rule because again, we have a 3x here. So using chain rule give me 3 dx. So let me go back to the integral and the substitute for secant. So I have tangent to the 4th power. So for now, I'm going to leave it. But secant squared becomes u squared. And the tangent 3x secant 3x dx, that becomes 1/3 du. So if I divide by 3 on both sides in the du expression. Right? So what do we do next? Well, definitely not okay to have a tangent 3x in there because we want the integral of u. So we can rewrite the tangent to the 4th power 3x. We can rewrite it as tangent squared 3x squared u squared. And then 1/3, I'm going to move it outside, du. And the tangent square, we can rewrite using secant square minus 1, because we know secant square is u. That will give us the integral of u. So that will be 1/3 integral secant square 3x minus 1 squared u squared du. And substituting for secant square, so I get u squared minus 1 squared, and I have a u squared outside du. And from here, we expand all the terms inside the integral before we integrate. So if you expand it using the formula, we get u squared squared, u to the 4th power minus 2u squared times 1, so 2u squared, and then plus 1. And don't forget, we still have a u squared outside du. From here, we distribute the u squared in there before we find the antiderivative, and then at the end, substitute for u. I have a quick question. Is it okay if I stop here? Okay, so 1 yes, 2 yes. All right. So I hope the rest makes sense, right? I'm sure you can figure out on your own. Just for the sake of using the time, I'm not going to go through all the steps. All right, let me see what the next question is. So 1 and the 3a, 1m. All right, so I'm going to go through 3a. All right, I apologize for going 1i. I got 1i. For going back and forth, I just want to go through following the order that people ask the question. So 1i. So 1i, we integrate dx over 1 minus 4x squared. So this problem, I think that's a couple of ways that you can approach it. One way is using partial fractions, because the denominator, we can rewrite this integral, but in particular the fraction in there, the 1 over 1 minus 4x squared, I can write as 1 minus 2x squared dx. This fraction in the middle here, I'm just going to rewrite it. You don't have to. So 1 minus 2x squared. I can factor the denominator because that's a squared. That's really 1 squared minus 2x squared. That's a squared minus b squared. You can factor it as a plus b times a minus b. So that will be 1 minus 2x times 1 plus 2x. And if I remember correctly, hopefully I'm not doing it wrong here. From here, we can try to find the partial fractions because the 1 minus 2x is a linear factor. The 1 plus 2x is also linear. So you can say a 1 minus 2x, b 1 plus 2x. And then we can try to find out the a and the b value from here. Again, there's a lot of ways you can go from there. What I do is I multiply by 1 minus 2x to all the terms. To find a. So I'm going to be a little bit lazy, so I'm just going to multiply by 1 minus 2x to all terms. And then I'm going to plug in x equals 1/2, because if x equals 1/2, we get 0 in the parentheses that I just multiply every term with. Right. So the left side here, I'm going to have 1 minus 2x, remember, cancels with the 1 in the denominator, so I just have 1 left in the numerator. And then 1 plus 2x is 1 plus 2 times 1/2. Maybe I should take 2 steps. So before I plug in x equals half, just multiply by 1 minus 2x to all terms. So I get 1 over 1 plus 2x on the left is equal to a plus b times 1 minus 2x over 1 plus 2x. Now, if I plug in x equals half, the b term will go away, become 0, right? Because the parentheses part is 0. So I get a, if I plug in half to the left, I get 1 over 1 plus 2 times half is 1. So a equals 1/2 as well. This is of the left side. Okay. What about the b? Well, we can use the same idea by multiply by 1 plus 2x to both sides. I'm not going to do all the steps, but I think if you plug in x equals negative 1/2, so I got b is 1 over 1 minus 2 times negative 1/2. B is also 1/2. I might be wrong, but double check the math here. So what do we
Sorry, I just had a question.
Yeah, go ahead.
if you do this out and you get to the point where you get over 1, you'll have 1/2 over 1 minus 2x and 1/2 over 1 plus 2x as like your substitute.
Yep.
When you integrate something over 1 plus 2x, you can use the natural log rule, right? But you have to also multiply by the derivative for the u.
Yeah, I forget. It's I think you have to divide by the derivative.
I just wanted to make sure that because if you weren't going to do it, then it might come up on the exam.
Yes. I never really memorized whether it's multiply by or divide by the derivative, but I'll show you. I think it's dividing. Because when you take the derivative, you always multiply by the derivative in chain rule, right? But when you integrate, you sort of doing the opposite. So I believe it's dividing, but I'll show you. So that's correct. So for me, I always take out half. So move the half outside. The first integral is 1 over 1 minus 2x dx. The second integral, again, I'm going to bring half outside. I get integral 1 over 1 plus 2x dx. So let's just say I'm going to take the first one, for example, the first integral here. So I'm going to say u equals 1 minus 2x du will equal to -2 dx. But I don't want -2 dx. I want dx to substitute into the integral. So dx is 1 over -2 du. So that's why.
Thanks. That's exactly what I was asking. Thank you.
Exactly. Right. So we'll be dividing by the derivative. And from here, so you end up with 1/2 integral 1 over u, but dx is 1 over -2. So again, I'm going to bring that 1 over -2 outside u. And similarly, you get something from the next term, and then you can go from there. Right, integral of 1 over u is natural log of absolute value of u when you substitute for u there. So this is a 1i. That's a great. So whenever you have questions, feel free to interrupt me and ask your questions. All right, the next one I'm going to go to 3a. So 3a, again, it's kind of like 3d. So we want to determine if the given integral from 2 to infinity sine square 4x divided by x squared plus 4 dx. We want to know if this is a convergent or divergent integral. We know it's improper because of the infinity, right? So graphically, you can think about area. So let's see whatever this function is. This is the sine square 4x over x squared plus 4. Doesn't matter what it looks like. So we want to know the area from 2 to infinity. We want to know this area. To be honest, I don't know how difficult it is to integrate directly, so I'm not even going to try because we're going to use comparison theorem, right? So we need to find function. For me, I immediately see that there's this sine square 4x. So I see sine square. I know that sine 4x or just sine x, doesn't matter, always has value from -1 to +1. So sine squared 4x will have value from 0 to 1 if you square any number from -1 to 1. But I want to know about sine square 4x over x squared plus 4. So I'm going to take everything, divide by x squared over 4. So basically now I have sine square 4x over x squared plus 4. The function given is less than or equal to 1 over x squared plus 4. Right? So that's good. So we have a function that we can compare with, which is 1 over x squared plus 4. So let me write down this function here. So this is 1 over x squared plus 4. It's bigger than the one that's given. So we can try to integrate it. That's totally fine. But noticing that this function 1 over x squared plus 4, the denominator has 2 terms. So maybe we can find a bigger function, bigger than this one, but it's easier, a lot easier to integrate. So I'm going to drop the 4. So remember, if we drop a term in the denominator, we get something bigger because we make the denominator smaller. So I'm just going to drop the 4. So we know that as a fact, 1 over x squared plus 4 is less or equal to 1 over x to the 4. So I'm going to use that function instead of the 1 over x squared plus 4. So I'm comparing this integral from 2 to infinity sine squared 4x over x squared plus 4 dx directly with integral 2 to infinity 1 over x to the 4 dx. So let me label that. So 1 over x to the 4 is here. How did you know to use the x to the 4? Oh, sorry, yeah. Thank you for Andrew and Sarah. Right, so it's, I don't know why I wrote x to the 4, it's x squared. We just dropped the 4. Now, how do I know to use the x to the 4? It's again, it's kind of just practice, right? I think if you stick with, I'm just gonna write on the side. So if you didn't figure out the 1 over x squared, if you just take this inequality, you can compare integral from 2 to infinity sine square 4x over x squared plus 4 dx. We know that's less than or equal to integral 1 over x squared plus 4 from 2 to infinity dx. This one, I believe you can integrate it, but it may not be an easy integration there. I believe it's possible to integrate. I think it gives you something like an inverse tangent or arctan, if I remember correctly. And then you can take the limit of arctan function at the end. And then you can still conclude whether it's convergent or divergent, I believe. But it's just from experience that whenever you compare with a function, if you can end up with some function that's really, really easy to integrate, always go for it. Especially in the case that when you have 2 terms in the denominator, right? Always try to drop 1 in the denominator to get something bigger if possible. Good question, but I don't think I answered your question, Andrew. So from here, we can just use p-test because of the p-value is 2. So p equals 2, which is greater than 1. That means this integral is convergent. And this is the bigger integral that's convergent. That means the one that's smaller than it, the one that we are interested in, this integral is smaller than the one that's convergent. So this one must be convergent. Again, you can think about the area, right? The area underneath this blue curve I draw here, that bigger area is finite because the integral is convergent. That means any area within this area must also be finite, which implies that the improper integral is convergent. All right, so that's 3A. So again, comparison test, generally speaking, if you have sine or cosine, try to use the fact that sine is from -1 to 1. If you have fraction has multiple terms in the denominator, try to drop one term in the denominator to get a new function. Or if you have multiple terms in the numerator, by dropping one term in the numerator. All right. So let me go back to the list. So I think I'm on 1M, and then a couple more questions in number 1. All right, 4 and 5, those are good questions too. All right, I'll try to kind of speed up the process. So 1M, we integrating. I think I'm having, so let me stop sharing the screen for a second, and then we share it. Okay, sorry about that. I was trying to see everything on my screen. All right, so 1M. So we have integral from 2 to 3, and then e to the square root x minus 2 dx. That's it, right? So, I mean, when you are given something like this, you're probably looking at it as like, what should I do? Well, I don't know, right? It's e leads to some function. It's not nice. We can't really try to, use integration by parts because of the exponential function there, which is not easy. So I'm just going to begin with u substitution, see what happens. I'm going to let u equals, there's a couple of things you could do. You could let u equals the x minus 2, this part, or you can let u equals the square root. So you probably try with u equals the x minus 2, and then later on you might have to try to use u substitution again. It turns out that in this problem, I'm just going to kind of try with u equals square root of x minus 2 directly. Or maybe should I do the other one? You know what? I regret. Let me take it backwards. I'm going to let u equals x minus 2 to make the integral a little bit better. So du equals dx. Now substitute in there, so I get a integral 2 to 3. Again, those are just x values. I'm not changing those yet. Keep those in mind. In fact, I'm not even going to write those. I'm going to come back to them later. So I integrate e raised to the square root of u du, basically. And I still have x from 2 to 3, but I'm going to write them later. Right now, I'm just focusing on finding the antiderivative. So what do I do now? I have e to the square root of u. Now, in this part, it's still not easy. So again, I'm going to let u, or should I be using u again? I'm going to let v equals square root of u to try to do the substitution again. So dv, this is the u to the half. So dv will be 1/2 u, sorry, dv will be 1/2 u to the negative 1/2 du. And the solve for du here. So I get half move to the left, give me 2. u to the negative half moved to the left to me u to the positive half, and the dv equals du. Basically, I'm using u substitution twice. And rewriting the integral, I have e to the square root of u, that's a e to the v, and a du, which is 2u to the half dv. I don't like u to the half there because I want an integral of v now. So I'm going to rewrite this u to the half with v. So I have, and I'm going to also move the 2 outside. So I have 2 integral e to the v times v and then dv. So that's what I get when I'm using u substitution twice. And it doesn't get me to the end because now I still have this e to the v, right, dv. So from here, it's actually a little bit easier because now we have e to the v function times v. This is kind of like e to the x times x. Then we can use integration by parts. By letting, I'm going to call this capital U equals v, and a d capital U, which is dv, and the d capital V, which is e to the v dv, and the capital V, which is just e to the v. Sorry for using those u and the v's, just a lot of substitution here. Just focus on this part using integration by parts. I'm going to leave the 2 outside. Again, I always leave those outside until the step I need them. So now I just focus on this integral. Using integration by parts, I have u times v, in this case, capital U, capital V. So that's a v times e to the v. Sorry, that's the lowercase. So v times e to the v minus integral v du. So that's a e to the v dv. Integrate it one more time. So I get v e to the v minus e to the v plus a c. We don't write that. So what do I have? The antiderivative is 2 outside times v e to the v. But now I'm going to substitute for v, right? It's lowercase v square root of u. So I get square root of u e to the square root of u minus e to the square root of u. But recall that u is x minus 2. So that's a 2 square root of x minus 2 e to the square root of x minus 2 minus e to the square root x minus 2. This is the antiderivative in terms of x. So now I can plug in the value for x. Remember that we begin with x is from 2 to 3. So x equals 2 to x equals 3. So now I can plug them in. Is it okay if I stop here? Because I think you should be okay to move on from there. Sorry, I'm being a little bit lazy in terms of completing the problem. All right. So that's what I did. In this problem, if you set, in the very beginning, if you set u equals square root of x minus 2, I believe you end up with the same parts that you will have to use integration by parts. If you change the limits as you went, or you have to change the variable back to x, or you keep them in terms of these. So good question. So this is a couple of things to keep in mind, right? So because what I did is that I use substitution to replace x minus 2 with u, and then using v somewhere in the middle. But at the end, so in this step, at the end, I converted everything back to x. Then it's okay for me to use the direct x value given in the beginning because everything is in terms of x, there's no problem plug them in, right? But if you let's say you set u equals x minus 2, then you figure out the corresponding boundary values in terms of u. So if you see, okay, x equals 2, u equals 0, x equals 3, u equals 1, right? And it depends on what you end up with. If you, at some point, you end up with this expression with u, and you want to plug in value there, you're going to have to use the u value from 1 to 0. So it really depends on what you want to keep. But if you say, what about I want to use v? Well, then you have to find the corresponding v value from here. So it takes square root of u. U is from 0 to 1. So v, again, takes square root is from 0 to 1. So you basically plug in v equals 1, v equals 0 there. Great question. So people have different preference, right? For me, I just like to keep everything in terms of x at the very end. But there's nothing wrong to plug in the v value or u value as long as you find the correct one. Good question. All right. So this is a 1m. We have 1j. 1j, I think, is a good question because it's a practice a different type of techniques that we haven't really done that today, but you definitely seen this before. So we have dx, integral dx square root 1 minus 4x squared. This is like if you rewrite it, it's kind of like a square root of 1 squared minus 2x squared. I'm going to rewrite that. Square root 1 squared minus 2x parentheses squared dx. So this is having like a squared minus x squared in the square root. I'm going to use trig substitution. So first thing, I'm going to draw a right triangle, call this angle theta. It's a 1 squared minus 2x squared, so the 1 will go on the hypotenuse. And the 2x, I'm going to put it on the opposite side. So I can have a sine. So sine angle theta is equal to 2x over 1, and just 2x. And then I can solve for x from here because I need to substitute for dx. So I can solve for x. So I get x equals 1/2 sine theta. From there, I can solve for dx, which is 1/2 cosine theta d theta. Right. So now you can substitute for dx, substitute for 2x or x. To make it less confusing, I always calculate the square root part first. So just looking at the square root, I got 1 minus 4x squared, or you can write as 1 minus 2x squared, doesn't matter. So that will become square root 1 minus 4 times x squared, which is 1/2 sine theta squared. And that will be square root 1 minus 4 times 1/2 squared is 1/4. Sine squared is sine squared. So I basically end up with square root of 1 minus sine squared theta. And you know that could give you cosine squared in the square root. We end up with absolute value of cosine theta. And to me, I always just assuming cosine is positive. So I just write cosine theta. But obviously, your professor or your instructor probably mentioned that you have to be careful with the angle theta because we want the cosine theta to be positive. We have to, if you look at the unit circle, cosine is x value. So basically we want this part like positive or 0. So we have to say the angle theta is from negative pi over 2 to pi over 2. But it's a indefinite integral, so that's the only case we're considering now. So if you just jump to cosine theta directly, I don't think there's anything wrong there for this process. So now we can go back to rewrite the integral. So we have integral dx we found is 1/2 cosine theta d theta, and the square root part gives us cosine theta. Right? Oh, that's nice. I hope I didn't do anything wrong, but okay, I'll take whatever I have. That's trig substitution, and then cross out the cosine theta and then move the half in front, so I get 1/2 integral d theta, and then we end up just 1/2 theta. You don't have to add anything there, plus a constant. Right? That's I did not know it was so nice. Anyway, that's a good thing, right? But we're not done yet. We given the integral is in terms of x, so we have to convert the angle theta in terms of x. This is a sort of a shortcut because we know that from the very early on when we set the substitution, when we set up the trig ratio, sine theta equals 2x over 1. Just rewriting it. So we had sine theta equals 2x over 1 2x. From here, we can actually solve for theta. So theta equals inverse sine or arc sine of 2x. And that's the substitution we're going to use at the end to convert all the expression in terms of x. So we get 1/2 inverse sine or arc sine of 2x plus c. So that will be an important step. Always at the end, convert everything back to sine, back to x. So that's 1j. Now we can go to number 2. All right, so 2b is the question there. All right, so just like I said before, if you have any questions, feel free just leave a comment there. So 2b, and then we can look at 2e. So 2b. Here we have integral dx over x squared square root 4x squared minus 1. So I'm just first look of this problem. I see this square root of 4x squared minus 1, just like in the previous problem. And that's kind of an indication that I might have to use trig substitution. It looks like direct u substitution wouldn't work in this problem because we don't have an x in the numerator. So I'm going to use trig substitution. I'm going to call this angle theta again. In the square root part, I have 2x parentheses squared minus 1 squared. So the 2x will be the hypotenuse here. And I'm going to put the 1 on the adjacent side. So that will give me cosine theta equals 1 over 2x. And I can solve for x from here. So I'm going to be a bit lazy by just moving the x to the left side and then divide by cosine. So I get x times cosine theta equals 1/2. So x equals 1/2 divided by cosine theta. That's like me being a little bit lazy there. You could move 2x to the left side and divide by 2. That's fine. So what does this give us? This is the 1/2 divide by cosine 1/2 times 1 over cosine. So that's a 1/2 secant theta. And I need dx. So dx equals 1/2 secant when I take the derivative of secant. I get secant theta tangent theta d theta. Hopefully I'm not making mistakes there. So that's the derivative of secant. And on the left side, the space I have, I'm going to calculate the square root of 4x squared minus 1 by plugging x value. So did I make a mistake here? Okay. Yeah, good question. So those are questions. How do you set up the right triangle? I think for now it's probably, for me, I kind of just memorize it, to be honest. There's like a no shortcut, but there's like in the process of memorization, you kind of have a little trick to follow. For example, let me just write it on the side here. So we only have 3 cases. One is a squared minus x squared, which is, I think it's the previous example. So if I have this, the a, well, it's a squared being subtracted from. So a will be the biggest side. So that will be a, the hypotenuse. Well, where do you put the x? You can put the x in the adjacent, or you can put x on the opposite. So I put the x on the opposite because I want to use sine at some point. If you put x on the adjacent side, you end up with cosine, which is fine too. To be honest, there's no wrong answer there. But the a has to be the hypotenuse. Right? So if I set up like this, then I end up with x over a equals sine theta. It's just a preference, want to have sine there. Now, in this example, I have x squared minus a squared basically. And then because x squared is being subtracted from, so the x has to be the hypotenuse. But where do you put the a? Again, there's no preference, but we, like people over the years kind of conclude that, oh, it's probably better to put it on the adjacent side. That way you end up with a secant, which is a lot easier to work with than cosecant if you put a on the opposite side. But again, there's no wrong answer there. It just depends on whether you are comfortable with secant or cosecant, right? So that will give you x equals a times y. We can go from there. So that's the setup. Now the last one is if you have a squared plus x squared or x squared plus a squared, doesn't matter. Now this case, it's not subtraction, it's addition. It's kind of like an a squared plus b squared equals c squared, right? In a Pythagorean theorem. So the a and the x has to be on the adjacent and the opposite sides. But how do you know which one do you prefer? It turns out that if you set x on the opposite side, a on the adjacent side, you can use tangent. But if you switch them, you have to use cotangent. It depends on how comfortable you are with cotangent. So x over a equals tangent theta. So again, a little bit memorization, but it's kind of you kind of have to use the the basically the Pythagorean theorem or various form of it to decide where does the x go, where does the a go. For now, I would say maybe just memorize it perhaps. Those are the 3 cases that will be useful. Like I said, a couple of times, it doesn't really matter. In some cases, you can put one known side to the adjacent or the opposite. It really doesn't make a difference. It just at the end, you might have an integral with cotangent that maybe less familiar with it, and then you don't know how to integrate. Good question. Yeah. So going back to this problem, so now we can figure out the square root part. So let me just do it quickly since we have done something similar before. So that's a 4 times x squared. X is 1/2 secant theta. So that's a 4 times 1/4 secant squared theta minus 1. So basically we get secant squared minus 1. So that's a tangent squared. So we have the positive part of tangent theta. I'm just going to assume tangent theta is positive in this case for now. And if you're not sure when tangent is positive, tangent is positive when you have sine and the cosine have the same sign. So basically, for the angle is from 0 to pi over 2, and also from 0 to pi over 2, that would be positive. Also from pi to 3 pi over 2. I think. So I'm just going to assume tangent theta is positive for some theta. And then now I can rewrite the integral. Which is dx. I have it as 1/2 secant theta tangent theta d theta. Divide by x squared. That's a 1/2 squared. So that's a 1/4. And the secant squared theta. And then the square root part just give me tangent theta. And we can cancel a few terms. The tangent goes away. The one of the secant will go away. The constant's 1/2 divided by 1/4. That's a 1/2 times 4. That's a 2. So secant cancel, tangent cancel. We still have a secant in the denominator. So 1 over secant theta d theta. Right? How do you integrate this? Well, I don't like secant, right? And then we only have one secant in the denominator. So what I'm going to do is I'm going to rewrite secant using 1 over cosine. So basically I have 2 integral 1 over cosine. So that's just cosine theta d theta. And from here, I believe that you can integrate it. So I'm not going to do much work there. Hopefully that's okay. All right, again, let me know if you have any questions on that. All right. So the next one is 2e. 2e is an excellent question on partial fractions. So I have integral x squared over x plus 2. And then I have x squared minus 2x plus 1 dx. Now this problem, I said, it's a good example for partial fractions. The reason I know that is because if I just kind of quick look, I know that U substitution probably not going to work because the denominator seems to be, a more complicated. It's a complicated a cubic expression, but it is a fraction, and the denominator has multiple factors. So I'm going to try with partial fraction. The first thing I have to do is I have to completely factor the denominator, the x squared minus 2x plus 1 term. So that will give me x squared over x plus 2 times x minus 1 squared, right? Now I can try to figure out the partial fractions. The first factor x plus 2 can be a denominator. So the numerator will be some constant a. But then I have x minus 1 as the factor. So x minus 1 without the square, that could be a denominator with b. And then because we have another x minus 1, So it wouldn't make sense to write x minus 1 again, right? Because that will be just the same as the second term I just wrote. But instead, x minus 1 square is a factor. So we're going to set x minus 1 square as the denominator. Now, what is the numerator? Because x minus 1 is a linear, so this inside the parentheses is a linear factor. So the numerator would be just a constant c. And we have to figure out a, b, and a c. So again, a couple ways you can go from here. I'm sure some ways are a lot quicker and make more sense to you, but I'm going to take the more systematic approach. So what I do is I multiply by x plus 2 to all terms to isolate the a. So I end up with x squared over x minus 1 squared equals a plus b, those terms, and then c terms, but they all have x plus 2 in there. Right, and then I'm going to plug in -2, so the b and the c terms will vanish. So I end up with a left, and then plug in -2, so I get 4 over -2 minus 1 is -3 squared, 9. So that's a. Right? How do we find the b term? Well, the b, I'm going to leave it for now because if I multiply by x minus 1, it doesn't really help. I still have x minus 1 on the left side and also for the c term in the denominator. So instead, I'm going to multiply by x minus 1 squared. So let me erase this. We're going to multiply by x minus 1 squared to all terms. So that will give us c by itself. So I have x squared over x plus 2 equals a term with x minus 1 squared, b term, well, b term just have x minus 1, but that's okay. And the c term, just the c, right? And I'm going to plug in 1 because 1 will make x minus 1 squared 0. So plug in 1, so the b and the a goes away. It doesn't matter because we already know what a is. But anyway, so those two terms will disappear. Give us c equals x squared over x plus 2. And then we said we plug in x equals 1. So c equals, if I plug in 1 there, so 1 over 3. That's c. But how do you find b? Well, the way I find b is I multiply by the denominator on the left side to all terms on the right side. You probably do that in the very first place anyway. So I get x squared equals a, which is 4 over 9. And then if I multiply the denominator over, I get 4 over 9 x minus 1 squared plus b times x plus 2 x minus 1, because one of the x minus 1 cancels with the denominator there. And then c times x plus 2. And I know c is 1/3. Right? So what do we do? Again, you probably learned the trick that you can plug in maybe x equals 0 there to find b. That's a quick way. But sometimes when you plug in x equals 0, it may not give you anything. Then you can try x equals 1. But what I do is I always expand this right side and then match with the left side. It takes a little bit longer, but it always works, especially if you have bx plus c in one of the numerators, or if you have multiple constants that you don't know, it's always good to expand and then match the terms. So I'm going to do it quickly. So this is a 4 over 9 times x squared minus 4 over 9 times 2x. So hopefully I didn't do any something wrong here. And then plus 4 over 9. And then the b term, when I expand it, I get b times x squared, if I FOIL those two terms first. And then minus x plus 2x, so plus bx, and then minus 2b. And then I have plus 1/3 x plus 2 over 3. So this is a more systematic way, and then I'm going to combine all the terms with the same x power. That's a 4 over 9 plus b x squared. And then the x terms, I'm going to put them together. So I have plus negative 8 over 9 x, and then plus b, and then plus 1/3 times x. So those are the, what I did is I take all the x terms, put the coefficients together, and then I'm taking all the constants, put them together. So I have 4 over 9 minus 2b plus 2 over 3. Oh my goodness, I hope I'm not making a mistake here, but anyway, the idea is that you expand it fully. And then the left side, we should also have x squared, x, and a constant term. We only have x squared, which is fine. We're just going to add 0x, add 0 for constant. And now we can match all the coefficients. So the coefficient of x squared on the left should match the coefficient of x squared on the right. So that means I have 1 equals 4 over 9 plus b. And the coefficient of x term should also match. So I have 0 equals negative 8 over 9 plus b plus 1/3. And then the constant should match. So I have 0 equals 4 over 9 minus 2b plus 2 over 3. Let me just quickly double check if it's right. So if I put 0 there, I get 4 over 9 minus 2b plus 2 over 3. Well, at least this equation is correct. The other two should be correct. So from here, we can solve for b. And it turns out that doesn't matter which equation you solve for b, you should only get one answer. What is that? So that's 3, 9. B is 5 over 9. Just quickly, like checking, I think the first and second equation give you the same. I'm sure the third one gives you the same b back. So this is the long way, but it always works. You just have to do a lot of expansion of the right side and then group the like terms. So now go back to what we have, right? We had the integral. So the integral, after we expand it, after we rewrite it using partial fractions, we have 4 over 9 divided by x plus 2. And then b is 5 over 9 divided by x minus 1. And then the last term, the last fraction is, let's see, c is 1/3 divided by x minus 1 squared. Yes. Let's double check. Correct. Right. So you just integrate each of them separately. I always, fractions are not nice, but just bring them outside for each integral. So I get 4 over 9, integral 1 over x plus 2 dx, and 5 over 9, integral 1 over x minus 1 dx, plus 1/3 integral 1 over x minus 1 squared dx. The first term, integral, give you absolute value, natural log of absolute value. Same thing with this one, you get something similar. The last one, you can use the U sub. It shouldn't take that long. All right, So I'm not going to finish it. I think it should be okay to finish it from there. So the next part is the 4 and 5. Those are two questions that was on the previous exam. But again, we see them here, but with slightly different functions. And make sure I'm not missing anything. 4 and 5. All right, so the next problem is number 4. So I think for the time being, I'm just going to set up the volume for and also area for each of this problem, and then maybe skip the integration part. So here we have, so we want to know the volume of the solid generated by revolving the region in the first quadrant bounded by the coordinate axis, the curve y equals cosine, and then for axis from 0 to pi over 2. So I'm going to draw the graph first. So cosine begins at 1, 0, 1, and then coming down, and then continues, right? But we're only interested in this part, pi over 2. So we want to know the volume when we rotate this area, like bounded between the x to y axis and also the curve. So A says we want to the volume. We want to know the volume when this area is rotated about y-axis. So there's two ways. One is the, obviously the disk method. The other one is the shell method. Because of this function, y equals cosine x, you kind of have to be a little bit careful in terms of determining which method to use, because one method might be easier to set up the volume, but it's not easy to integrate. For example, I'm going to show you. So the first approach, let's just see we rotating about the y-axis. Let's see we want to use the disk method. So we're going to slide the disk horizontally. So the volume is equal to integral of the volume of one disk formula, which is the pi r squared times the thickness, right? So that will be pi times the radius squared. And this is the radius. So the radius, I'm going to call it just x for now because it's from x equals 0 to some x value stop on the curve. So pi r squared, so pi x squared. And the thickness, which is dy. Right? But what is x here? Because we want to integrate with respect to y, we have to replace the x there. And the x here, you can bring the pi outside, but the x, we don't know. We know y equals cosine x, so that means x equals inverse cosine of y. So you can put it there. Square dy. And then the boundary value you can put in there because we integrate with respect to y, so we need two y values. So y going from 0 to 1. So this is the y equals 0. This is the y equals 1. There's nothing wrong with writing like this. This is perfectly correct, what I wrote. But the problem that say you want to actually figure out the volume, I don't know. It's very difficult to actually integrate a cosine inverse function, an inverse cosine function. So my point is that this approach will give you a formula for the volume, but it's not easy to integrate. Right? So what we're going to do is that we're actually going to try to use the shell method. So this is using disk. It's not nice. I'm going to use shell method. So again, we have this area 1 pi over 2 cos y equals cosine x, and then we're rotating about the y-axis. So we're going to use the shell method, which says we're going to take 2 pi times the radius, that will give us the circumference, and then multiply by the height and then the thickness of the shell, which is 2 pi radius times the height of the cylindrical shell, and then the thickness. Well, 2 pi for now. Now, what is the radius? Remember, I'm rotating about the y-axis. So imagine this small rectangle when we rotate about the y-axis, we end up with this sort of cylindrical shell here, right? So the radius is the distance from this y-axis go all the way to the curve. So this is the radius. Again, it's the x value, right? It's from x equals 0 to some x value that stops on the curve. So that's the radius, it's just x. Now, what about the height? The height is this part in green. That you can think about is from y equals 0 to some y value on the curve. So I'm going to use y for now. I'm going to have to replace it soon. But for now, let's just call that y. That's the height. And then what about the thickness? Well, the wall of the shell is in the x, the thickness is in the x direction. So I'm just going to call it dx. So that gives me an integral, but has x, y in it. But we are integrating with respect to x, so I don't need the y. So the next step, I'm going to rewrite it by replacing y with cosine x. So we get 2 pi x cosine x dx. So that's all good. And we have to write down the boundary value. Here we integrate with respect to x. So we need to look for the boundary values in the x direction of the shaded area. So the shaded area covers from x equals 0 to all the way to x equals pi over 2. So from 0 to pi over 2. This is the volume. This one obviously is not nice, but you can actually integrate it. So if we move 2 pi outside, 0 to pi over 2, we end up with x cosine x dx. This integral, we can find the antiderivative by using integration by parts. Kind of like x times e to the x, so it's the same idea. So we're going to let u equals x, du equals dx, and then dv will give us cosine x dx. And the v we can find out by integrating cosine x, give us just sine. And then go from there. I hope it's okay if I leave it here. It will be good practice for you to practice integration by parts. Why is it three terms, not cosine? All right, so did I write something wrong? So in the integral I have, right over here, when I set integration by parts, the x becomes u. Now the remaining part, the cosine x dx, this part will become dv, right? Because the integral is u dv form. So x is u, the remaining part will be dv, cosine x dx. And when I integrate that to find v, yep, so that's how we end up with sine. That's okay. Those questions are good because any confusion you have, other people will have it. Don't worry. Good. All right, so I'm going to move on to B. B says we're going to take the same region, but this time we're going to find the volume by rotating the region about x equals half. Sorry, x equals pi over 2. So again, I'm going to quickly draw the region here. One pi over 2, and I'm going to rotate about the line x equals pi over 2. Oh, sorry, I did it completely wrong. Negative, so it's positive pi over 2. So we rotate about this line. Again, from previous example, we know that this method doesn't work. In this case, if you want to use washer method, it also doesn't work. So we're going to use shell method. So to use shell method, I'm going to take one vertical rectangle. I'm going to rotate about this axis, so I end up with this shell. But the axis of rotation is different now. So the volume equals, again, 2 pi times some radius times the height times the thickness. Now, what is the radius in this part? Right? The radius is actually the distance from this curve all the way to x equals pi over 2. So that's the radius. How do we figure out the expression for that? I'm going to write on the side. So the radius of the cylindrical shell is the distance between the most right x value, which is pi over 2. So between x equals pi over 2 and the x on the curve. So I'm just going to put in a quotation, the x on the curve. Right? So that's the radius. How do you write down the mathematical expression? We can just write the radius as pi over 2 minus x. So that will be the expression for radius. So note that this is the x equals pi over 2, the blue dotted line, and the point, the x value on the curve is this x. It's some x value is not fixed, it moves, depends on where the point on the curve that we have. Depends on where the skinny rectangle you draw, right? So you have a different x value, but in general, we just call it x. So now we can put it in the integral. So that's 2 pi times pi over 2 minus x. So that's the radius. Now, what about the height? The height of the cylindrical shell is going to be this part. It's from the x-axis, go all the way to this some y value. So you can say, well, it's going from y equals 0 to some y value. Right. So the difference is just going to be y. Now, what about thickness? The thickness, just like a previous problem, it's in the x direction, right? The wall is in the x direction. So we're just going to write dx. Again, we don't like the y here, so we have to rewrite it. So that would be exactly right. So Andrew, that's correct. So the height or the y because so here when I see y or x, I'm talking about that point on the curve, right? On the given curve, y equals cosine x. So y is cosine x. Good point. So 2x pi over 2 minus x, and then cosine x. So substituting for the y dx. Good point. It's the height. Right? So now we integrating with respect to x. So the boundary values will be in the x direction. Doesn't matter where the axis of rotation is. We're still going to look at the shaded region for x intervals, so which is from x equals 0 to pi over 2. So those are the boundary values. Again, if you want to integrate this, so, oh, sorry, that should be 2 pi, not 2x. So I'm going to move the 2 pi outside, 0 to pi over 2. And then we have pi over 2 minus x multiplied with cosine x dx. You can split the integral into 2, or you can just leave it as 1. But either way, at some point, you're going to have to use, just like before, you're going to have to use integration by parts. Maybe calling this u equals pi over 2 minus x, and you can find du from there. And the dv will be the remaining part, cosine x dx. And then we can figure out the b from there. So the rest is just like a normal integration by parts problem. Don't forget you have a 2 pi outside. Just carry it in every step. You don't have to involve 2 pi in integration. All right, so that's this part. The next one is OC. So again, we have the same region. But now we rotate this piece about the line y equals 1. So y equals 1 is right here. So imagine that we're rotating about that dotted line and then create a solid. So here you kind of have to decide whether you want to use the shell method. Again, if you try it, you probably end up with something that you don't like, or maybe use the washer method or this method. Again, it's so I don't try to memorize a specific rule as to which one to use. I just kind of try it. If it doesn't give me something nice, I try the other one. So if I kind of quickly sketch the solid here, so I have this sort of 3-dimensional shape. Outside is a cylinder, but in the middle there you have this cone that's being missing. Right? So you can use the shell method, or you can use the washer method. So I'm going to use the washer method in this case, because from what I did, I knew that a washer method will work because I have the thickness of the washer, or the height of the washer is in the x direction. So I don't need something with y. It's good to have something with x. So that's a washer in the middle. I'm just going to make it a little bit thicker. So a washer method, basically it's a disk method, which is volume equals pi times the radius squared times the thickness or the height. Right? But how do you find the radius? The radius here is, I'm going to try to use a different color to make it obvious. So the radius, I should be careful. So for a washer, the radius squared is actually the difference of the two radius squared. I should have made it clear in the first place. So radius squared in terms of a washer is the radius big squared minus the radius small squared. Because we remove a volume in the middle, right? So you kind of have to subtract the volume in the middle. All you can think about is the big circle area minus the small circle area. But if you take out the pi, so you end up with the radius square being the difference of the squares of two radius. I hope that didn't confuse you more. I apologize if I did. So what's the bigger radius? The bigger radius is from this axis of rotation all the way to the outside of the solid, which is the x-axis. So that's a bigger radius. So R big is just equal to 1 because it's from y equals 1 to y equals 0. Now, what about the small radius? The small radius is not clear, but if I kind of zoom in here, then I'm going to go back. So the small radius is from the axis of rotation, so all the way to the curve. So this difference in blue, hopefully that makes sense. That's the small radius that I'm removing in the middle of that disk, right? So what is the difference between that? What is that distance? Well, that's the difference between y equals 0 to some y value on the curve. So I'm going to write R small is equal to the difference between y equals 1 and some y value for now. And I can put in what y is. So y is, and recall that y equals cosine x, so 1 minus cosine x. Now I can put those terms in the volume integral. So that's pi radius square. Again, it's the difference of the squares of two radius, right? So that will be R big, which is 1 squared, minus R small squared, which is 1 minus cosine x. That's R small squared. And then that's the radius squared, R big squared minus R small squared. And then we have thickness. The thickness of the washer is in the x direction, so I have dx. And the boundary values of integration, it's just, again, we integrate with respect to x, we look in the x direction of the shaded region, which is from 0 to pi over 2. So that's the washer method. And from here, you can take out the pi and integrating 1 squared, which is 1 minus, you can expand this, I'm just knowing from experience that if you expand the 1 minus cosine x squared, you get another one which will cancel the one that's already there. So that's a 1 minus 1 minus 2 cosine x, and then plus cosine square x dx. So distribute the negative, the 1 will cancel, give you pi. Again, you still have those boundary values. I'm being a little bit lazy not writing them. So you get 1 cancel, give me positive 2 cosine x. And then the cosine square is negative cosine square x dx. You can split the integral into 2. So the first one will be pi integrating 2 cosines, and we bring the 2 outside, so get 2 pi integral cosine x dx. The next one, which is pi but it's minus, so minus pi integral cosine square x dx. The first integral, I believe that you can find it easily, but what about the second one? How do you integrate cosine square x? The trick is that the exponent of cosine is even. So we're going to have to use the double angle formula to rewrite it. This is what I call the double angle formula. Your teacher could probably call it differently. So the cosine square x, let's just focus on only this integral part. Just leave the pi outside for now. This part is integral 1/2 1 plus cosine 2x dx. So make the 1 minus cosine squared into 2. Yes, correct. So Marcus, that's a good question, and the Jeremy's response is correct. If you have a square outside, you cannot write as a sine squared. That's a very good explanation. Yeah. Good, excellent. So from here, you just have to keep splitting the integrals. So again, you can move the half outside combined with the pi. So you get negative. I'm just going to, bring the negative pi down there. So I get negative pi over 2 integral 1 plus cosine 2x dx. And you can integrate the 1 separately from the integral cosine 2x, right? And then each of them should come out nicely when you integrate. Okay. Oh my goodness. All right. So that's the number 4. We have a few minutes. But I understand that foiling is not easy. It's very easy to make mistakes because you get multiple paths, right? I would say, drawing arrows really help. Just don't need to rush. Just, use some arrows, say, oh, go from here to there. Just step by step. Take your time. That way you get less mistakes. All right, so I'm going to move on to number 5. Number 5, we take the region bounded by the curve y equals natural log of x, looks like this. And y equals 0, which is the x-axis, and also x equals e, this one. So we basically take this region, and then we're going to rotate it. Well, the first part, we're going to find the area. Now, if you remember, area is just summing up all the rectangles, right? So if we see we have this rectangle, we have another one, we get a lot of them, they're very skinny, we add up all of those rectangles, we get the area. So area is just integral of, for rectangles, it's base times the height, but the base is the sort of the width of the rectangle. So that's just going to be dx, the way I draw the rectangle. And what about the height? Well, the height is this is the height, right? It's the distance between the y value on the curve and then the y equals 0, the x-axis. So I'm just going to see y for now. What is y? Y is natural log of x. So we're just integrating natural log of x dx. from two values. It's in the x direction. So from this first point and the e. What is the first point? Well, the first point you're going to have to know from experience the x-intercept of natural log of x give you x equals 1 from previous experience. So that's from 1 to e. How do we evaluate this integral? If you have a natural log, obviously you can memorize a special formula for integral of natural log, but you can use integration by parts relatively easily. Well, I shouldn't say easy, but it works well. So we're going to say u equals, it's always try to get rid of natural log, so let u equals natural log of x, du equals 1 over x dx. And the dv is the remaining part. Well, if we take away natural log of x that is equal to u, we only have dx left. And the v is just equal to x. And it turns out that this will give us u times v, so that's the x natural log of x minus v du. So that's the integral. Sorry, v is x, du is 1 over x dx, so the x cancel, just give us dx. And don't forget that we're evaluating from 1 to e for all of them. So that's the x natural log of x minus just x evaluated from 1 to e. And the natural log of e is 1. Natural log of 1 is 0. So if you put those terms in there, you should be able to get a final answer. If not, just plug them in and leave them the way it is. So that's the area for A. Now B says find the volume of the solid formed by revolving this region about the x-axis. So I'm going to redraw this. So here we're taking this region, this area. This is the x equals 1, this is e, and then we're rotating about x-axis. So that gives us the solid. Right? Now, if based on what you did before, obviously it's easier to use the disk method. So imagine that we have this disks that we stack them together. So the volume is equal to pi radius squared times the thickness. So pi radius squared times the thickness. There's no part that's missing. That's good. So that will be integral pi radius. What is the radius? The radius is the distance from the highest point, the point on the curve, to this x-axis. So that's what I'm going to call y. So y squared, y being the radius. And the thickness is in the x direction, so that's dx. The next step is to rewrite the y there. So we get pi, y is natural log of x. So y equals natural log of x given. So natural log of x squared dx. And then again, the boundary values are from 1 to e. Okay, so what do we do from here? All right, it's a couple of things I guess you can do. You can try to use integration by parts again by calling this part u, that's dv. I didn't fully work out this problem, but I tried integration by parts seemed to work. You might try another approach. To be honest, I'm not confident if it works, which is you can try U substitution, which probably isn't going to work out well. So I'm going to stop. I'm just going to say integration by parts. You might have to do it twice. Because we kind of running out of time, so I'm not going to do that. But again, practice integration by parts. The process should be similar to the one above. If you have questions on this, you can stick around and I'll explain it after everyone leaves, after 8. Now the C part is that we're going to find the volume by rotating this about the line x equals -2. So again, so here we have this area, and then we rotate about the line x equals -2, which is on this side. Oh, okay. That's a good question. So, well, actually, since you're asking, so let me just kind of show you the beginning step of integration by parts there. So integration by parts, it's always a natural log that's give you a problem, right? But whatever, so in this function, the natural log of x squared, that's actually together as one term, not like, separate terms. So I was thinking about doing by setting u equals natural log of x squared, and then dv will be dx, and then v equals x du. Maybe this is where I'm going to get into trouble. Perhaps not. So du will be 2, using chain rule, 2 natural log of x times the using chain rule, the derivative of natural log, which is 1 over x dx. Right? And then from there, the integral will give me u times v. So that's the x natural log of x squared. That's okay. That's all good. Minus the integral of v du. So if I take x multiply with du, so I get 2 natural log of x, 1 over x, multiply with x, and then dx. So the x cancels, give me 2 natural log of x remaining. If I do it correctly, yes, x cancel 2 natural log. So this x cancels, and then the 2 I can put it outside. So I basically have this. And then this integral, I'm going to have to use integration by parts again. That part, I'm going to call it capital U, which is natural log of x. And the d capital U I can find out. And then the d capital V, I'm going to call it just dx. And the capital V I can find out to be x. And well, we basically have done that, right, in the previous part. So that's what I meant integration by parts twice. Good question. So yeah, so whenever you have a natural log in the integral, perhaps try with integration by parts. Sometimes U substitution works. I have seen, I forgot which problem it is. I think it was 2U there, and also 2V. So note 2U and the 2V. Those two problems, a U substitution will work. You don't even need integration by parts. So use U sub by letting U equals natural log of x. I'm just saying, like some problems, the U substitution works when you set U equals natural log. Sometimes it doesn't work. You might have to use integration by parts, but you want to get rid of the natural log, right? So set U equals natural log in those parts. Good question. So let me finish this last part, then I'll finish. It's already 8 o'clock. If you have more questions, you can stick around and ask, okay? But if you have to go somewhere, feel free to go. This will be recorded and made available to you later. So here we take this region, right? That's a 1. This is the natural log of x, y equals, and then we're going to rotate about the line x equals -2. So we end up with something on the left side. I'm just going to draw it here. So I'm sure that you can try to picture this. So you get this like a cylinder on the outside, but in the middle you have this shape that's missing. Right? So which method are we going to use? This one you can try to use a washer method. If you do that, now I'm not going to finish it, but I just want to quickly point out the issue you might run into. So if you use the washer method, you're going to have horizontal washers, right? So before we do any work, let's just look at it. This washer method. Obviously, it's okay to find the radius, the big one and the small one, but I want you to kind of think about the thickness of the washer. The thickness is in the y direction, right? So that means you're going to have an integral of dy in there. But the problem is that at some point you might have to convert y equals natural log of x in terms of y, which is totally fine. It's not impossible. And in fact, actually, this is the approach that I think it's the correct approach. So that's kind of the beginning work, the dy. So let me kind of finish this. So v, using the washer method, integral pi times some radius square. Again, it's the bigger radius square minus the small radius squared, pi r squared, and then times the thickness. And then what is the r big and what is r small? Let me just show it on the side here. Let me erase this. So the bigger radius is from the axis of rotation, go all the way to the outside of the solid. Doesn't matter where you draw that, it's always going to be this distance. So r big equals the distance between the most right value is x equals e. That's always a constant. And the most left value is x equals -2. So the bigger radius is just going to be e minus -2, which is just 2. I'm sorry, just e plus 2. So that's a bigger radius. Now, what about the small radius? The small radius, again, is from the axis of rotation, go all the way to the inner part of the solid, I guess the part that's being removed. So r small is equal to the distance between, well, this x value. What is this x value on the right? I don't know. That depends on where the point is, right? I'm just going to call it some x value. And the most left x value is always -2. So the smaller radius is just going to be some x value minus -2, which is x plus 2. So those are the two radius that we're going to need. So let me put them in the integral I have. So the r big squared, so that's a e plus 2 squared, minus r small squared, so that's a x plus 2 squared. And the times the thickness. Remember I said that for the washer, the thickness is in the y direction, so dy. Right. we can't integrate this. This is the problem because we want to integral in terms of y, but we have x in there. So we have to replace the x with y. So this x, we have to rewrite it using y. Well, we know that y equals natural log of x. Can we solve for x from there? Yes, we can, right? So we can solve for x, so x equals e to the y. So that will give us the sum x expression to put in there. I'm almost done, last line. So that will be pi e plus 2 squared, just treat as a constant. I know it's not nice, but just treat it as a constant. So e plus 2 squared is a constant. You can expand it because at some point you're going to do some cancellation perhaps. Minus e to the y plus 2 squared dy. So that's the integral for volume, but don't forget I didn't finish. Now, what is the boundary values? Again, we integrate with respect to y, so I'm looking at the boundary values for y. So the lowest y is 0, the highest y is this top point. So this is the highest y value right here. That's when x equals e, when x equals e, y equals 1, right? And then the lowest y is just y equals 0. The highest y is 1. So we're integrating from 0 to 1. Those are the y values. I'm going to do one more line, 2 more lines, and I'll stop, I promise you. So the pi, I'm going to move it outside. Integral 0 to 1. I'm going to expand every term there. You don't have to, but you might find it easy. So we have e squared. So e plus 2 squared. So that's a plus b squared. Give you a squared plus 2ab plus b squared, right? So we have e squared plus 2 times e times 2. That's a 4e plus 2 squared, which is 4, minus the next part, e to the y squared, that's the e to the 2y. And then 2 times e to the y times 2, that's a plus 4 e to the y, but I'm subtracting it, so it's minus. And then minus 4, so the 4 and the negative 4 cancel, which is now okay, dy. The pi is still outside. We get e squared plus 4e. Those are the constant terms. There's no y, no x, nothing, so they're just constant. And then minus e to the 2y minus 4e to the y dy. So my last comment is that this is a constant. Doesn't look nice, but it's just treated like a pi or some constant. When you integrate, just put it outside. They're not part of integration. This part, you can use the U substitution if you like to integrate. The last part, you basically just integrating e to the y directly. All right. So on that note, this is 0 to 1. I'm going to finish the review session. If you have any questions, feel free to stick around for a few more minutes. But I know that you probably have other stuff to do. All right, take care, everyone, and good luck. Make sure you go to your TA or professor's office hours tomorrow if you have more questions. All right, take care. I'll make sure this is online for you. All right, I'm going to stop sharing.